Welcome everyone. We are standing at the dawn of a new era in artificial intelligence, one in which autonomous, goal-driven software agents plan, make decisions, and act on our behalf. These agentic systems aren't just chatbots, they are autonomous entities designed to execute complex workflows without continuous human intervention. Our mission today is to demystify the risks they introduce and to show how the OWASP Top 10 for 2026 can guide us towards safer, more resilient AI systems. We'll identify the critical risks, understand how Agentic AI works, and implement defenses that keep security by design and by default at the forefront. Imagine software that can not only answer questions, but break big tasks into plans, call APIs, access databases, and remember context across sessions. That's an agentic system. It reasons in plans, uses tools and services, and maintains memory to act autonomously. This autonomy is powerful, but it introduces new attack surfaces. The integration of large language models has massively expanded the scale and capability of agents, exposing them to vulnerabilities far beyond simple prompt injection. Our job isn't to fear these systems, but to understand them, because their growing presence across finance, healthcare, and everyday applications makes their security everyone's concern. Before diving into the threats, we need guardrails. The first is least agency. Constrain an agent's autonomy so it has only the permissions and tools strictly necessary for its task. The second is strong observability. Maintain deep visibility into an agent's reasoning, tool usage, and outcomes. And for high-impact actions, always keep a human in the loop. These principles are our compass. They ensure that as agents become more capable, we remain in control. OWASP's Top 10 for Agentic Applications is a comprehensive framework for understanding the risks we face. The list includes: first, agent goal hijack. Attackers redirect agent objectives. Second, tool misuse and exploitation. Over-permissive tools used in dangerous chains. Third, identity and privilege abuse. Escalation through delegation chains. Fourth, agentic supply chain vulnerabilities. Compromised third-party tools or plugins. Fifth, unexpected code execution. Unsafe code generation leading to remote code execution. Sixth, memory and context poisoning. Corrupted long-term memory affecting future decisions. Seventh, insecure inter-agent communication. Spoofing or tampering between agents. Eighth, cascading failures. Local errors amplifying across workflows. Ninth, human agent trust exploit. Social engineering via trustworthy sounding agents. 10th, rogue agents. Autonomous drift leading to misalignment. We'll explore each along with the defenses that make agentic systems robust. First, agent goal hijack. Agents act based on a mix of system prompts, user input, and memory. In a goal hijack scenario, attackers manipulate the prompt, context, or training data to override original instructions. Untrusted emails or web content carry hidden directives like ignore previous rules that cause plan drift and ultimately harmful actions. Symptoms include sudden shifts in conversation topics, attempts to access tools outside the allowed scope, and unexplained data egress. In the real world, a shopping agent might be silently redirected to exfiltrate pricing or customer data instead of completing your order. Defenses include isolating system prompts from user data, inserting human approval for high-impact tasks, and validating an agent's plan before execution. Second, tool misuse and exploitation. Autonomous agents often have access to email, databases, cloud APIs, even shell commands, powerful tools that can be abused. When an attacker triggers goal drift, the agent begins chaining tools in unsafe ways, sending emails, pulling data, and executing commands with destructive outcomes. The result can be financial loss, data leakage, operational downtime, and compliance violations. As human security notes, even authorized tools can be misused, leading to spend spikes and large-scale scraping. Mitigation starts with least privilege. Scope each tool to the minimum necessary permissions. Add human-in-the-loop approvals for sensitive actions, and enforce rate and cost limits to keep any single agent from running amok. Third, identity and privilege abuse. Identity is messy when agents delegate tasks on behalf of users. If agents inherit broad read-write access when they only need read, cache credentials for days, or pass requests along chains of other agents, attackers can piggyback on that trust. This confused deputy problem turns agents into unwitting insiders. Without separate identities and session boundaries, enforcing true least privilege is impossible. The remedy is to treat agents as distinct principals. Give them their own service accounts and audit logs. Agent X on behalf of user Y. Use just-in-time credentials that expire after a task, require step-up authentication for sensitive operations, and define fine-grained allow lists instead of wildcard permissions. Fourth, agentic supply chain vulnerabilities. Agents don't live in isolation. They compose third-party tools, plugins, templates, and connectors. If any of these dependencies are compromised, the agent becomes an autonomous attack vector. Malicious plugins may masquerade as helpers but exfiltrate secrets. Compromised model context protocol servers can inject bad data. Poison knowledge bases can feed lies to your agent. A classic example is the Trojan tool, a seemingly harmless utility that, when invoked, solves a math problem but secretly siphons environment variables. According to industry analysis, because agents rely on a constellation of tools, the real risk is buried in the internal supply chain. Defensive strategies include maintaining software bills of materials, SBOMs, verifying cryptographic signatures on tools, isolating third-party executions via sandboxing, and rigorously reviewing new plugins before adoption. Fifth, unexpected code execution. Some agents write code to fulfill requests, an extremely powerful capability when harnessed safely. But if an agent blindly runs code it generates, in Python for example, a clever attacker can inject malicious commands and pivot to a full remote code execution. OWASP warns that this is the bridge from weird AI behavior to classic system compromise. Human security echoes this, noting that prompt injection and unsafe loops can turn innocent requests into RCE. To defend against this risk, always run generated code inside short-lived, isolated containers with no network access. Use syscall filtering to limit kernel capabilities and require explicit user confirmation before executing any generated code. Sixth, memory and context poisoning. Agents build long-term memory from conversations, retrieve documents, and vector databases. Attackers poison this memory by injecting malicious data, which the agent later retrieves as facts, causing persistent misalignment. The effects can last beyond a single session, spread across users, and create hidden triggers or logic backdoors. Human security notes that poisoned memory persists across sessions, leading behavior to drift gradually rather than in one obvious step. Mitigations start with sanitizing all data before storage, segregating memory per user or tenant, using integrity checks to detect modification, and expiring old memories quickly. Recognize the poison cycle: injection, persistence, retrieval, impact, and break it. Seventh, insecure inter-agent communication. In systems where multiple agents collaborate, communication becomes a target. Attackers may spoof messages to impersonate trusted agents, capture and replay valid instructions, or tamper with content in transit. Without authenticated and encrypted channels, agents may authorize payments or run actions based on forged requests. The solution is a secure protocol stack: mutual TLS to encrypt the channel and verify identity, signed messages to prove origin and integrity, nonces and timestamps to prevent replays, and semantic validation to ensure messages make sense before acting on them. As the OWASP guidance notes, never trust an agent solely because of its network location. Always verify its identity and intent. Industry experts echo this. Multi-agent systems require authenticated, encrypted channels to prevent spoofing and tampering. 8. Cascading failures. Autonomy means agents can trigger actions on their own, but it also means errors can propagate at machine speed. In a cascading failure, a single local error, hallucination, or poison input doesn't stay local. It amplifies across interconnected workflows, causing systemic instability. You may see request storms flooding APIs, runaway token usage causing cost explosions, or entire systems crashing. Human security warns that a single misconfigured policy can ripple through a network of agents, leading to widespread outages. To build resilience, implement circuit breakers that halt processing when error rates exceed safe thresholds. Enforce bounded loops and autonomy caps to limit the number of steps or actions per task. Compartmentalize agents so a failure in one domain can't crash another. And design compensation actions such as rolling back transactions or alerting humans when confidence drops. 9th, human agent trust exploit. The most insidious attacks exploit our trust. Agents are authoritative, articulate, and helpful. Attackers use that halo effect to trick users into approving harmful actions. The threat sequence goes like this. A malicious instruction is hidden in user input. The agent rewrites it into a polite request, and the human approves, believing it's routine. Attack patterns include polished previews that look safe but execute malicious code, false urgency that pressures users to bypass checks, confirmation bias, where users reflexively click OK, and authority bias, where they assume the AI has already checked security. Human agent trust exploitation is already happening. As human security notes, many damaging incidents stem from a human clicking approve without realizing the origin of the request. To defend against this, adopt risk-tiered approvals. Auto-approve low-risk actions like search or summarization, but require step-up authentication and clear context for high-risk actions such as transfers or code execution. UX must show why the agent wants the action, not just what it wants. 10th, rogue agents. Sometimes the agent itself becomes the problem. Rogue agents don't crash. They continue operating but deviate from their design intent, pursuing hidden sub-goals, hallucinating new objectives, or optimizing for harmful metrics. Because they possess legitimate credentials and tool access, their actions look like valid employee behavior. Detection requires establishing behavioral baselines and watching for anomalies in resource usage or unusual tool sequencing. Human security describes rogue agents as the AI equivalent of insider threats. Only continuous monitoring reveals the drift. Controls include emergency kill switches to sever access immediately, autonomy budgets that cap steps, API calls, or financial spend, and state resets that periodically wipe context to prevent accumulated drift. In essence, treat agents like powerful employees with strict supervision and offboarding procedures. Now that we've surveyed the threats, let's talk about building resilient systems. Security scales when multiple layers work together. Least agency means agents operate with only the permissions and tools necessary to complete their intent. Strong observability gives total visibility into reasoning chains, tool inputs and outputs, letting you detect drift before it becomes a breach. Tooling controls. Scoped allow lists define exactly which tools an agent may invoke. Rate and cost limits prevent denial of wallet attacks. Sandboxing isolates side effects like file system or network access. Identity controls. Distinct agent IDs ensure you never share user credentials with agents. Short-lived tokens minimize the impact of leaks. Step-up authentication engages humans for sensitive actions. Data and memory controls. Auto-classify data sensitivity before ingestion. Redact PII or secrets from context windows and sign memory entries to detect tampering. Communications controls. Sign messages, check freshness with nonces or timestamps, and restrict which agents can talk to whom. Operational controls. Keep humans in the loop for high-risk tools. Deploy circuit breakers to stop cascading failures instantly, and run anomaly detection to flag intent drift or unusual tool chains. These layers work together to make agentic systems trustworthy even as they evolve. We've journeyed through the OWASP top 10 risks for agentic applications, from goal hijacks to rogue agents. The threat landscape is broad, but not insurmountable. Key takeaways include: inventory your agents and tools. Give agents distinct non-human identities. Restrict tool access to what is essential. And review approvals with human oversight. Implement sandboxing, secure communications, monitoring, and cost guards. Practice advanced defenses like memory hygiene, circuit breakers, red teaming, and behavioral baselines. Set measurable goals such as 100% human approval for high-risk tools, incident response in under an hour, and zero uncapped spend events. As we wrap up, remember, Agentic AI is a transformative technology. With thoughtful design and layered defenses, we can harness its potential while protecting ourselves from misuse. If this episode helped you navigate the new frontier of agentic security, please subscribe, hit the like button, and leave a comment with your thoughts or questions. Your engagement helps us continue creating content that keeps our community safe and informed.